Okay, in this video we're going to talk about composite functions. Composite functions are an extremely important concept in algebra and in particular in calculus. So it's important to understand how they work. So we're going to look at here the basic concept of how a composite function works using the good old function machine. Alright, so you'll remember from algebra what the function machine does is it takes a value x, inputs it into a function, and outputs the value of that function. So we're now going to double up our function machine. Alright, we want to find the composite function f of g of x, so we input x into g, we output g of x, and then we take that value and input it into f, and that outputs g of x. Alright, so if we're given two functions, f of x and g of x, we want to find the composite function f of g of x. So I've got two functions here. F of x equals 2x squared minus 3, and g of x equals 4x. So my function machine for g is going to multiply my value of x by 4, and my function machine for f is going to take twice the square of a value and subtract 3. Right? So now what I want to do here is I want to find f of g of 1. So that means I'm inputting 1 into my function machine for g. Alright, so I pop that in, and what pops out is 4 times 1, which is equal to 4. And now 4 is the value that slides into the f function machine. And what pops out there is 2 times 4 squared minus 3. Alright, 4 squared is 16, times 2 is 32, minus 3 is 29. Alright, so this tells me that f of g of 1 is 29. Alright, that right there is the basic idea of evaluating a composite function. Alright, now, we've got some notation here. Alright, there's two different types of notation for composite functions. This first one up here, f o g of x. Now the o is kind of like a multiplication dot, only an open circle. Sometimes this is referred to as fog for obvious reasons. Alright, so f of g of x this way, this notation is more formal. Alright, you'll see this in textbooks when they're stating a problem. In the instructions, find f o g of x, because it's a little neater in line for a textbook to write. Alright, so this is the nice formal notation. The second form down here, which is what I used on the previous page, f of g of x, is actually function notation. This is more practical. This is what you're going to use when you are when you are working a problem out. Alright, the two are equal. F o g of x is exactly the same thing as f of g of x. Alright, so again, up here, this is what you're going to see in textbook instructions, and this second one is, again, the more useful notation because it really tells you what to do. Alright, so we're talking about functions. Functions have domains. Some functions have restricted domains. And if I'm given two functions and asked about the domain of the composite function, I need to know how to find that. Now, it would be nice if I could just take the domain of f and take the domain of g and smush them together and say that the union of those two is the domain of the composite function, but it's not. Alright, and let's take a look at why. So, first of all, let's write down the domain for f. F is going to be the set of all x where we have to exclude the point where the denominator is 0. Alright, so that means x is not negative 2. Alright, because if I put negative 2 in here, negative 2 plus 2 is 0. Right. Over here I get something similar. It's a set of all x such that x is not 1. Right, because 1 is the point that if I put it in there, the denominator will be 0. Now, here's the thing. The if I want to do the composite function f of g of x, all right, that's the composite function I want to look at. First of all, I want to think about what that's going to look like. All right, so let's take a look at the notation. F of g of x, right? F of g of x. That means that in f, in place of the x, I'm putting g of x. So what does that mean? That means 1 over g of x plus 2. All right? In its most basic form, that's what that composite function is saying to do. Now, I already know over here that x cannot be negative 2. All right, so that means whatever is in that spot cannot be negative 2. So that means when I write it this way, I end up with the set of all x such that g of x cannot be negative 2. Because if g of x is negative 2, then that denominator is 0. All right, so to write the domain of the composite function, I need to find that point where g of x is negative 2. And so the easiest thing to do is to take g of x, right, 4 over x minus 1, and set it equal to negative 2. All right, now this is just a proportion, so I can solve it easily by multiplying both sides by x minus 1. When I do that, I get 4 on that side, and I get negative 2 times x minus 1 on that side. All right, so that's 4. That's negative 2x plus 2. All right, if I bring this over here, I'm going to subtract 2 from both sides. So that means this is 2. This is negative 2x. Divide both sides by negative 2. And I get x equals negative 1. All right, so g of x, right, let's throw a g of x over here, equals negative 2, where x equals negative 1. So that makes the domain of my composite function the set of all x, so that x is not equal to negative 1. All right. All right, so finding the domain of a composite function given the two individual functions is a little more complicated than just squishing together the two domains that you've already got. All right, so now let's actually look and see what the domain, what the composite function f of g of x looks like. All right, so if I need to find f of g of x, all right, we've already seen that that means I'm taking f and replacing x with g of x. All right, but now I actually want to put g of x in there. So this becomes 1 over g of x, which is 4 over x minus 1 plus 2. All right, so there's the first step in finding the composite function. Now I've got a complex fraction that I need to simplify. I'm going to do that by multiplying the numerator and denominator by x minus 1. All right, now I'm choosing x minus 1 because it is the common denominator of all the pieces of my complex function. And when I multiply the numerator by x minus 1, I get x minus 1. When I multiply the denominator, notice when I multiply this term by that term, the x minus 1's divide out, and I'm left with a 4. And when I multiply x minus 1 times this term, I get 2 times x minus 1. Alright, so I can come down here and I can simplify this a little bit. Let me cheat down here a little bit. This becomes 2x minus 2. Alright, so on top I get x minus 1. And on the bottom I can combine the 4 and the minus 2 and I get positive 2. 2x plus 2. And then the last thing I can do here, just to make my point, is to factor the 2 out of the denominator. Alright, so I end up with f of g of x equals x minus 1 over 2 times x plus 1. Alright, and if you notice, what's the domain of this function, right? It's the set of all x such that what's going to make this denominator 0? Well, negative 1. Okay? So you can see that that matches with what I had up here, right? We did this work over here to show that the domain was going to be all x such that x was not equal to negative 1. And by actually forming the composite function, I was able to confirm that. Alright? Alright, so you know how to put composite functions together, how to form one. Let's look at how to recognize one. Now, one of the important things you're going to have to do in calculus, both Calc 1 and Calc 2, both differential and integral calculus, is to be able to recognize composite functions, because there are techniques that are necessary for both of those classes that involve having to recognize composite functions. Alright, so I've got three functions up here, h, g, and f. Let's start with h. If I wanted to split f of x and g of x so that h of x was equal to f of g of x. Alright, so I'm using g as the inside of the function and f as the outside of the function. If I'm going to recognize it that way, then what's inside is x plus 1. And then you want to ask yourself, what am I doing to x plus 1? Well, I'm raising it to the 50th power. So that means if I were to plug g into another function to have it be raised to the 50th power, that other function would have to be x to the 50th. Right, let's move over to g. Right, again, I want to do the same thing. I want f of x, and I want g of x, so that capital G is equal to f of g of x. Alright, so again, I'm looking at what I'm plugging into f is g of x, so that would be, again, the inside portion here would be x squared plus 4. Okay? What am I doing to x squared plus 4? I'm taking the cube root of it. So if I had to write a function f so that when I plug x squared plus 4 into it, I get the cube root, it would have to be the cube root of x. Alright, one more. Alright, again, I want f of x, and I want g of x, so that capital F of x is equal to f of g of x. Alright, now this one's a little trickier, but we can still use the same idea. Alright, I've got this denominator here. If I make that my g of x, alright, then what would f have to be? Well, what am I doing to g? I'm saying 1 over g of x. So that would make my f 1 over x. Alright, now the idea of being able to recognize a composite function and then pull it apart is only going to work with very specific types of composite functions, and those are the ones that have essentially an inside and an outside. Notice that wouldn't work very well with this. Right? I can't really look at that and say I have an inside and an outside, even though it was formed by composing two functions. Alright, so the ones that we're interested in being able to recognize are the ones that have a clear inside part and a clear outside part. Alright? Okay, so basically composite functions involve taking one function and sticking it inside another. Right, in the next video, I'm going to talk about inverse functions, and inverse functions make use of this idea of composite functions, so you can go on to that video next.